my course on fundamentals of electrical engineering. This is the last session in transformers. We dealt with two sections in transformers. In the earlier section, we were talking about efficiency, regulation, hysteresis laws, eddy current laws, all those aspects. In this section, we talked about mostly the two important constructions of transformers. One is the auto transformer. Second is, of course, the three-phase transformers. Okay, there are certain ideas which were not fully perhaps were taken up in the earlier session. So this session is more or less like a mop-up. Can also be called as a consolidation of some of the ideas that may be required. Okay, the first problem itself happens to be something to do with three-phase. Okay, so there are other aspects also coming into the picture. So let's see what this one tells us, or what this one requires out of us in a gate exam context. Okay, so we see there is a transformer, there is a star connected winding on the primary A, B, C, and N, and there's a switch there. Okay, on the secondary side with a small ABC there, the windings are can be delta connected. If S2 is closed, it can be a delta connected version. Okay, in the other case, it's a star connected version, no doubt about it. But the neutral is connected or not is decided by the switching of S1. Okay, so let's read the problem. So I suppose it's very clear. The picture is very obvious. We have a star delta transformer. So long as switch is closed, S2 is closed, S1 if it's closed, the star point is connected to the neutral as well. Okay. So let's read the star delta transformer shown above is excited on the star side with a balanced 4-wire. Okay, it's a 4-wire system, 3-phase sinusoidal supply voltage of rated magnitude. The transformer is under no load condition. Okay. With S2 closed, this is important, with S2 closed and S1 open, the current waveform in the delta winding will be what? Okay, so we'll have, so the options are sinusoidal at fundamental frequency, flat top with third harmonics, only third harmonics, none of these. Okay, so now we are having S2 closed and S1 open. Okay, so when you are having such a situation, okay, what is possible is that in the delta which is connected, there is a possibility for third harmonics to flow. Okay, that's it opens a possibility, but no third harmonics flow on the star side because there is no connection to the ground. Okay, or neutral. Okay, in this case we are having a delta which is giving us a possibility for the third harmonics. Okay, so long as there is some kind of non-linearity coming into the picture, though it's on no load, it's a possibility that there can be what is called as some kind of constructional differences which can give rise to non-linearities. In that case, the only true quantity, the only true option is that there is a possibility. Okay, so only third harmonic currents can flow inside the delta. Okay, so no other currents flow. Okay, because it's not loaded. Okay, let's look at the second part of the question. With both S1 and S2 open. So what has happened when S1 is open? So earlier S1 was open. Now also S1 is open, but S2 is also open. Now it's not a delta. Okay, or in other words, it has become completely unbalanced. Okay, so there's definitely a possibility of having harmonics. Okay, so let's see. The flux waveform will be a sinusoid fundamental frequency, flat top with third harmonics. Okay, definitely it's a third harmonic kind of situation, but flat top as well. Okay, so it's a dangerous situation there. So let's move. Okay, so we are learning something. That's all. Okay, so it's not as okay. So this is a problem wherein we have a field kind of understanding, because in the field they only talk about transformers in such a language. So let's read the language. We are having a star connection on the primary side and a delta connection on the secondary side. By now, this recognition is very deeply ingrained in your mind, is what I hope you have. As was mentioned earlier, capitals are shown on the primary side and small letters are shown on the secondary side, and the windings are shown as A2 A1, B2 B1, and C2 C1 on both sides. Okay. Yeah, so what is three single-phase transformers are connected to form a three-phase transformer bank. The transformers are connected in the following manner. Okay, so what is this configuration is what is asked. Okay, so when you use the first letter will be capital. Okay, when you're using this kind of nomenclature, it's just a nomenclature. The transformer connection will be represented by it's to represent the transformer. Okay, so the first letter will show the primary. Okay, that's why it is put in capital. So what does it say? Either it says D, in which case it's a delta, or it will say Y. Okay, so primary will be given first. It will be in capital letter and it will represent whether it's a star or delta. Okay, obviously it's a star, so that's the reason why Y, WYE or Y is shown there as the first alphabet and in capitals. The next alphabet will show the secondary, and it will show in a small letter, and small y will represent a star connection, a small d will represent a delta connection. Okay, so we are having a D there. So YD is true for all aspects, so that's okay. Okay, now the angle difference between them. Okay, so how do you specify the angle difference? If there's no angle difference, it will be like a 12 o'clock clock. Okay, so in a 12 o'clock situation is when the small needle and the black and the big needle match each other. So why D0 is not true? Why? Because we know that on the star side there is an angle of lead. Okay, that is so okay. So if that is so, then we see that star side will represent the big needle, and the delta side will represent the lag, which has a position at 1 o'clock. Okay, so it will show 1 o'clock, which means that there's a 30 degrees difference, because the total degrees is 360 in a 12-hour representation on a clock. So each of these hour quantities will talk about a 30 degrees. So YD1 will adequately represent the nature of the transformer that is perhaps locked inside a box. Y will show the Y will show that is it's a star connection, and the capital will show the primary. The small letter will show the next letter will be in small letters, which will show which will show the secondary, and the alphabet Y will show a star, and the alphabet D will show a delta. Okay, and then we come to the clock kind of representation of the angle between the primary and the secondary. Okay, so in this case we realize that the line voltage in the primary, because we can compare only line voltages, because the delta has the phase voltage and the line voltage as the same. Okay, so we can compare the line voltage. We see that we are having the line voltage leading. Okay, or in other words, because the primary will represent a capital or the big needle, the small hand will show the small needle will show it as a 1 o'clock because of the 30 degrees phase difference. Okay, so that's it. Okay, 11 o'clock will mean a lagging situation. Okay, okay, so let's go to the third problem. Okay, here we are having again 3 windings. Okay, and we see that on the high voltage side, A, B, C are capable of the terminals A, B, C are capable of delivering voltage to the three-phase voltages to 3 windings. Okay, but at the same time there are 2 switches, S1 and S2, just as in the earlier case. These are subtle differences that we are having, and S1 will connect or will not connect C to this. Okay, and S2 will short the middle coil. Okay, so that's what we see. On the secondary side, we see that they are all connected in star. Why? Because you can see that the second part, the second terminal of each of these windings are connected together. Okay, and the first terminal is going to receive, it's going to be connected to the load. Okay, so ABC, that is capital ABC, are supposed to lead the currents or lead the phases into the delta connected version, okay, of the primary. Okay, the secondary is delta star connect. Okay, so that is what you got to notice first. What is the kind of connection? Okay, and what are the switches doing? The switches are either shorting or either supplying the phase C also, that is S2, S1, and S2 is going to short out the short out the winding connected between B and C. Okay. Okay, so let's see. Figure shows a delta. Okay, as we guessed, delta star connected 3-phase distribution transformer. Okay, you can also read and not waste time, but of course, recognition at the first instance is going to be a very big empowerment for people who are wanting to write gate examinations. Okay, distribution transformers used to step down the voltage from 11,000 to 415 volt line to line. So 11,000 by 415 by root 3 is going to be the transformation ratio between the primary and the secondary. Okay, 11,000 is on the primary. That's a delta connection. On the star, we are having 415 volts, so 415 by root 3. That's going to give us the transformation ratio. Okay, it has 2 switches, S1 and S2. Under normal conditions, S1 is closed. Okay, so that's how we normally run the transformers, because we want to give all the 3 phases. Okay, S1 is closed and S2 is open. Okay, because we don't short out windings. Okay, under certain special conditions, S1 is open. Okay, so we are now, what are we doing? Let's see what we are doing. Okay, and S2 is closed. In such a case, S2 is closed means it's shorting the winding. Okay, and when you are opening, not only are you shorting the middle winding, you're also connecting B and C together. Okay, and A is already connected to. Okay, so that's two things are happening. One is that two windings are going to be connected in parallel. That is, if you call the first winding as A and the second winding as B, which is going to be shorted out, and then you are having the third winding C, then A and C are now going to come in parallel, okay, by virtue of operating both the switches wherein S1 is opened and S2 is closed. Okay, so this also needs to be realized or recognized. Okay, in such a case, the magnitude of the voltage across the LV terminals A and C. Okay, so what is A and C? A and C happen to carry the voltages which are going to be obtained from their primaries. Okay, B is not going to get any voltage because it's shorted out. Okay, I suppose that's clear. That is the middle coil on the secondary coil is not going to get any voltage because no voltage is going to be induced in it. Why? Because the corresponding coil is shorted. On the other hand, A and C are connected. Coil A and coil C on the primary are parallel with respect to each other by just simply opening out S1 as also closing or linking B and what should have been C together. Okay, so there are two coils in parallel, and on the other side you are again having voltages which are equal in both the coils. There is coil A, that is the secondary coil A, as also secondary coil C. Okay? Coil B is having no voltage. Okay, so what is asked is, we want to know the voltage between A and C. Okay, so S1 is open and S2 is closed. Okay, middle coil on high voltage side is shorted and bottom coil connected parallel to AB, as was mentioned earlier. Okay, so both coils now have 415 by root 3 on the secondary side, because 415 phase voltages are 415 by root 3, and both of them are going to have 450 by root 3 on the side. Hence, voltage across AC is going to be so. And then you are going to talk about A and C, which are now going to have a which are in phase, because they are using the same voltage A C along. They are using the same line to line voltage, but of course the transformation is going to be 415 by root 3 because phase voltage is appearing. But there are two of them. Why? Because they are in phase and because they are using the same voltage for transformation. Okay, so we see that the voltage is the same, is equal to 2 into 450 by root 3, because 450 by root 3 is the phase voltage. But there are two of them because they are obtained from the same winding, that is from the same source. Okay, from the same line voltage AB and AB. So A is connected and B is connected to C. So the same voltage AB. Okay, so that's it. Okay, so I suppose the magnitude is 2 into 415 by root 3 is the same as equal to 480 volts. Okay, very simple. Okay, just the understanding is important. In all these problems, the understanding is what is important. Okay. The fourth problem is wherein we are having a three-phase delta star transformer. Okay, so delta star is now going to have a voltage divided by root 3 situation there. Supplied is 6000 volt on the delta connected side. Okay, that's the phase voltage and the line voltage. The terminal voltage on the secondary side when supplying full load at 0.8 lagging power factor is 450 volt. Okay, so it's supplying a load at 0.8 power factor lagging. Okay, the equivalent resistance and reactance drops for the transformer of 1% and 5%. Now, what is the turns ratio of the transformer is what? That's what is asked. So per phase. Okay, so now we need to have so it's only supplying the voltage. Okay, so it's not actually the voltage at the secondary. It is supplying at 450 volt. Okay, that's the voltage at the terminal. Is the terminal voltage, and then this voltage is across a 0.8 lagging power factor load. Okay, so far so good. So let's see per phase drop in the transformer. Okay, so now we are trying to find out the drop in the transformer. Why? Because this drop is mentioned as 1% and 5%. Okay, so we are having 415 by root 3. Okay, so there is so we are having in the resistance drop. Okay, of course, because we are having a 0.8 power factor lagging, so it's going to be 1% into 0.8. Okay, by 415 to root 3 we are finding out the secondary. Okay, so we are trying to find out 415 by root 3 is the voltage there, and then it is having a drop across a load which has, okay, it is drawing a current as such that it has a resistance and a reactance drop of 1% and 5%. So 1% will take the 0.8 power factor, that's why 1 into 0.8, and 5% will take the complement of it, which is going to be 0.6. So 1 into 0.8 plus 5 into 0.6 will give you, and that multiplied by 450 415 by root 3 will give you 9.1 volt as the total drop in the resistance and reactance associated with the transformer. Okay, so that's so 415 by root 3 is chosen as the base, and then 1 into 0.8 plus 5 into 0.6 will all align everything along the horizontal axis. So the total drop is going to be 9.1. This now has to be added to 415 by root 3 because that's the terminal voltage. That will give you the secondary voltage. That is 415 by root 3. So it will give you the secondary voltage of the transformer. Okay, so that's equal to 248.7. Okay, so 248.7 happens to be the phase voltage, which is also because it's on the star. So you can multiply by root 3 such that you can compare both. Okay, or you can have face-to-face ratio of 6000 divided by 248.7 because that's more appropriate, and that will give you 24.12. So that from amongst the answers you can pick out 224. Moving on to the fifth problem. Two transformers are to be operated in parallel such that they share load in proportion to their KVA rating. This is different. Okay, so they are supposed to share load in proportion to their KVA rating. There we have a rule. Okay, so that rule will be stressed upon. Okay, the rating of the first transformer is 500 KVA, and its per unit leakage impedance is 0.05. Okay, if the rating of the second transformer, so they should share based on their rating. Okay, so the second is half. Is having only half the rating of the first transformer. It's only 250 kVA, and so what's its per unit leakage reactance? So what's the rule? Okay, so both deliver load currents in proportion to their ratings. It means that if their per unit reactances are same on their own rating, okay, that the answer is going to be 0.25. Okay. So we come to the sixth problem. So let's look at the sixth problem. Okay, so this is also a sharing of transformers, the sharing of load by two transformers, two single phase transformers, T1 and T2, each rated at 500 kVA. Now we are having an equal rating capacity, are operated in parallel. Percentage impedance of T1 and T2 are 1 plus J6 and 0.8 plus J4.8. Okay, please remember, see that if you multiply both 1 plus J6 by 0.8, you get 0.8 and J4.8. So this must be useful for you. Okay, so this is the way that you plan your answers. Okay, to share a load of 100 kVA at 0.8 lagging power factor, the contribution of T2 is asking. So what is T2's share? Okay, so it's just like okay, the voltage is the same. So what is going to happen? Current division is going to matter. Okay, so current division is exactly the rule that's going to being utilized. Okay, so how do you use the current division? If you want to have T2's share, it should be multiplied by T1's impedance and divided by the total, the combination. So what is T1's impedance? 1 plus J6. Okay, so 1000 is what is going to be shared. So 1000 kVA into 1 plus J6 divided by 1 plus J6 plus 1 plus J6 plus 0.8 plus J4.8. So what is that? 1.8 plus J10.8. Okay. So simply take out 6 from. So simply take out. So you can simply take out 1.8 from here. So you can, because you see 1 plus J6 on the numerator, just take out 1.8. So the first quantity becomes 1, and 10.8 divided by 1.8 is going to be 6. So 1 plus J6 cancel. So you see that 1000 divided by 1.8 is equal to 555.55. So only the recognition of the fact that we are having 1 plus J6 and 0.8 and 4.8, and when you add them together, you can simply take out 1.8 such that already you see that when you multiply by 0.8, there is some relation. But of course, it's current division rule. Why? Because we are having what is called as the voltage is going to be maintained same because they are operating in parallel. So only way that they can share the load will be such that current division rule applies. What is current division rule? 1000 kVA, which is to be shared, has to be multiplied by the other impedance, which is 1 plus J6 divided by the total. So we are having 1.8 plus 10.8. Okay, so just see if 1.8 goes in both. You see that it goes because that's already indicated. So you see that it's going to be 1000 divided by 1.8 because 1 plus J6 cancelled from the numerator and the denominator. Very simply you can do the problem. Okay, so let's go to the seventh problem. The following arrangement consists. Okay, so what do we have there? Wx and Yz. And the transformation ratio is 1:1.25, and there's only a resistor there. Okay, so let's see, there must be something nice here. The following arrangements consist of an ideal transformer and an attenuator. So attenuator is simply a resistance kind of thing which is just like a potential divider. Okay, you take out what you require. Okay, which attenuates by a factor of 0.8. Okay, so you can attenuate whatever voltage is obtained by cutting it down to 0.8 times the voltage which is made available at the secondary of the transformer. Okay, so an AC voltage V Wx1, that is the first time that's applied, is equal to 100 volt. It's applied across Wx to get an open circuit voltage Vyz1 across Yz. Okay, so after attenuation, okay. Next, an AC voltage Vyz2 equal to 100 volt is applied across Yz. Okay, so first we apply 100 volt across, let's say, call it primary, and then it gets reflected on the secondary using the transformation ratio, and then it's cut down to 0.8. Okay, so that's what is happening in the first case. The second case, what is happening is that you're giving 100 volt directly to the attenuated portion, so it doesn't build it up. Guess what happens is this voltage becomes available across the secondary, and then it is going to be built up in the primary. Okay, and that ratio is going to happen. Okay, so that's the major difference between. Okay, so how it's a one-way kind of wall. Okay, so what happens one way is that whatever voltage you impress on Wx becomes transformed to secondary, and then it gets attenuated. On the other hand, if you apply a voltage to Yz, it becomes available across the secondary winding, and then using the transformer ratio, it's available across the primary. That 0.8 doesn't figure. That's all. Okay. Okay. Let's see what is required. Yeah. So yeah, an open circuit voltage Vwx2 across Wx. It gets a voltage because of the transformation. Then Vyz1 by Vwx1, comma Vwx2 by Vyx2 are respectively. Okay, so there's a ratio in both cases. Okay, so let's start with the first one. Okay, so let's try to find out Vyz1 when 100 volt is applied, and then you are having a transformation ratio 1 is to 1.25. So you are transforming it to, that is the voltage on secondary is larger because the ratio is 1 is to 1.25. So it becomes 100 into 1.25. Then it gets attenuated by 0.8. So the voltage that is available across Vyz1 when 100 volt is applied across Wx is also equal to 100. Okay, so one of the answers should be 100 by 100, and there we see that B and C happen to be 100 by 100. Okay, so either B or C is right. Okay, now let's talk about applying a voltage 100 here and on Yz, and so what happens is that this 100 voltage is now available across the secondary, and so it reduces to 1 by 1.25 on the primary, and that is what is going to be Vwx2. We call it 2 because of the second instance. Okay, so 100 divided by 1.25 gives us 80. Okay, so what is going to be the ratio? 100 is applied, so 100 is okay, so and 80 is obtained, so 80. Okay, since we are always putting, we are putting Vwx2, so Vwx2 is only 80 divided by Vyz2. Vyz is, we are applying 100, so 80 by 100. So option B is correct. I hope this is clear. This is just an attenuator being able to progress in a forward direction. It has no role in the reverse direction. Okay, but the transformation ratio applies. Okay, in both cases. Okay, so moving on to 8th problem, we are having a coil with a current source being connected to it, and the one is to it looks like an isolating transformer, and there's a switch across the switch there. And what is asked is the circuit diagram shows a 2-winding lossless transformer with no leakage flux excited from a current source IT, whose waveform is also shown. Okay, the transformer has a magnetizing inductance of 400 by pi millihenry. So L is equal to 400 by pi millihenry. If the waveform of IT is equal to 10, so it's a sinusoidal one. Though a triangular waveform is shown, perhaps it's for the next case. Okay, so if the waveform of IT is equal to 10 sine 100 pi t ampere is applied, the peak voltage across AB with S closed. Okay, so what is the voltage available across the transformer is what is going to be asked, because that is going to be applied across the resistor. Okay, so AB is the voltage across the transformer secondary as also the load. Okay, so that's what is asked. So it's simply L di by dt. What is L? 400 by pi. What is di by dt? We are having 400 by pi multiplied by, if 10 is there, then di by dt gives you cos, of course, and then omega comes out, which is equal to 100 pi. Okay, and then this, of course, 10 raised to minus 3 because of the millihenry aspect. So we see that the all put together 400 by pi, 10 into 100 pi into 10 raised to minus 3 gives us a voltage as equal to 400 volt. Okay, so that's the peak voltage that we are getting, because it has the sign quantity. The sign quantity is intact. Okay, we are not supposed to divide by root 2, and what is asked is peak value. What about the second part of the question? In the second part of the question, we are having a current being applied Okay, and that's the waveform which is shown for IT. It's a triangular waveform, and the peak voltage across AB with S open. Now S is open, and we want. Okay, so how do you do that? Okay, so for that, what we have to do is that we have to remember that in this case we have to find out di by dt. So what is di by dt? We have to take what is called as the slope. Okay, so let's take the peak values are, so we have to take the maximum value. Okay, so what is the peak value? We see that it's equal to 10. I suppose the height is, for the triangle, the height is obvious, it's equal to 10. Okay, and what is, and 10 occurs over 5 milliseconds, so di by dt is the same as equal to 10 by 5 into 10 raised to minus 3. 10 raised to milliseconds, so 10 raised to minus 3, or 10 by 5 into 10 raised to 3 is going to be di by dt. This you have to multiply by L, okay, because L di by dt is still true. Okay, so what is L? That's equal to 400 by pi. Okay, so 10 by 5 gives you 2, and 10 raised to 3 and 10 raised to minus 3 become cancel each other, so 400 pi multiplied by 2 is giving us 800 pi as the answer, and that's option D. Okay, so option A and option D happen to be the answers. Moving on to the ninth and the last problem. What is there? The core of two-winding transformer is subject to the magnetic flux variation as indicated in the figure. Okay, yeah, so we are having EPQ of 100, and then there's a flux. Okay, and the winding sense is also shown. Okay, the winding sense admits the flux in the same direction, and the winding nature is 100 is to 200. Okay, and then we apply the flux here. Flux pattern is shown, looks like a trapezoid. Okay, the induced EMF in the secondary winding as a function of time. Again, LdI by dt. So what do we see? LdI by dt in the earlier portion would be L is, of course, yeah, we have, or n d phi by dt. So n is there, 100. Okay, either LdI by dt, which is the same as equal to LdI by dt. So in this case, it's n d phi by dt. So 100 is there. D phi by dt is, we can see d phi by dt means, okay, there's a rise. So the total rise is 0.12 divided by the time value, which is equal to 1. So 100 into 0.12, that's giving you, that gives us, so the secondary voltage is what is asked. So 200 into 0.12, that gives us 24 volt, and it remains constant. And then what happens is that when you are having a flat top portion for the flux, there is no change in flux, so d phi by dt is equal to 0, so it goes to 0. That is, the total voltage goes to 0. Okay, so that's where, so you see that this applies. The answer is true in option A, because we are having 24 volt, and then it's a pulse. Okay, and then it goes to 0. Okay, and then when the flux waveform starts to descend, okay, again it descends, the total descent is in 0.5 seconds. Okay, and the descent value is of 0.12. Okay, so again n d phi by dt, and then n is again 200, because we are looking at the secondary only. That's where the voltage is being mapped. So we are having 200 multiplied by 0.12 divided by 0.5. So it's going to be larger. Why? Because the whole thing has happened in a shorter time span of 0.5 seconds, unlike in the early case where we had 1 second. Okay, so the voltage is going to be 48, and it's going to be negative. Why? Because the slope is downward, or the slope is negative, because it's sloping down. Okay, so that's all that's there. Mostly we discussed about waveforms, etc. I hope the general trend of questions that may not be in the same class as we have been discussing earlier may also come, but then you have to be careful. You have to just follow the waveform. You may have to, okay, and you have both aspects being utilized, L d by dt or n d phi by dt. But of course, when you're talking about the waveform, the ascent will give a positive value for the slope, and the descent will give you a negative value. So those things need to be considered, and you'll be very fine.